thank you very much for the invitation. It's unfortunate that I'm not physically there, but you know, it's a new life, and but I get to see people in the place that I typically don't have a chance to go. So I guess it's plus and both positive and negative, and I get to see new people in this way. It's very nice. Okay, so I'd like to tell you the project that we're doing and about finding gravitational wave from the early universe. So this talk is about going to be about the cosmic microwave background. So let us remind ourselves how they look in the sky. So this is the Milky Way, and we're going to project this in the so-called galactic coordinates, so that we can see the whole sky on the screen. So we expand the sky around. So that will be the full sky. Then we go from visible to longer wavelengths. We have visible, near infrared, far infrared, sub-millimeter. But by the time you go to the microwave, the whole sky is completely filled with uniform 2.7 Kelvin microwave. That's cosmic microwave background, the fossil light from the Big Bang. But then you start improving the sensitivity of your detector by a factor of 100,000, that you would start seeing microkelvin level fluctuations on top of 2.7 Kelvin background. So this is the temperature anisotropy of the cosmic microwave background. But there's also residual galactic emission in the galactic plane that we would have to somehow remove. Then, now that's the image here. So x-axis is both time and distance. It's a light cone. We're observing sky or universe along our light cone, and this would be the oldest light we can ever see, because before this, universe was too opaque to see directly by light. If you had neutrinos, gravitational waves, you can see a bit farther near the beginning. But the question is, okay, this is as far as we can see directly by the light. Can we go beyond, right? Can we go beyond this and learn more about the earlier universe? Right, this is when the redshift was 1000, temperature of the universe was about 3000 Kelvin. Well, that's pretty early universe, but can we go beyond? Okay, so how do we do that? We use laws of physics to do it, but it's too complicated to explain, certainly if we wanted to do this in a seminar for general public. So we decided to create a movie. Now, we are scientists who do research, and we want to communicate our exciting scientific discoveries to the general public who support us by paying tax. But we often fail. We fail miserably because we're not trained to do this kind of outreach, although we are supposed to do it. So I had this very interesting experience in Japan. I visited Kavuri IPMU in the University of Tokyo, where we had a workshop for science communicators. It's still general public, but people who do curators at museums, people work at planetarium, poets, artists, singers, musicians, and movie director. And one of the audience was indeed this movie director, Mr. Kosaka, who was pretty famous for producing very high quality full dome movie in planetarium domes. So he was inspired by talk so much that he started to produce the world first movie on the cosmic microwave background. It's super high quality. Humans are real actors and actresses, but everything else is computer graphics. We even have the original music. And this was produced both in Japanese and English. The Japanese version has been shown at several planetariums in Japan. English version has been also shown, for example, in Montreal, Shanghai, sorry, not Shanghai, Hong Kong, and hopefully more and more planetarium in the world will start showing them. We also presented this to the some of the international competitions and got very good recognitions, or very much happy about that. Now, if you Google the horizon beyond the edge of the visible universe and YouTube, you see the trailer. Unfortunately, the full version of the movie is not yet available online, but maybe in the future we might be able to show it. But I wanted to show a bit of the movie so that you can get some idea. Now you have to imagine it's a full dome movie. You're going to see now the circle here, and middle is the zenith, so it's top of your head. And this is the front, this is the back, side to side. So you have to imagine that in your head, okay? So there you go.
The cosmic background radiation is the wall at the edge of the visible universe. We cannot see directly the further past beyond this wall. But these temperature fluctuations may tell us what happened in the further past.
The conditions beyond the wall of the cosmic background radiation could be thought of as a liquid with high temperature and high density. You could say it was like a hot soup. Something happened behind this wall that made waves, which can be seen in the fluctuations in the cosmic background radiation. There must have been a grand sound that shook the universe. We can learn a great deal about the universe if we can extract this cosmic sound. The origin of the sound would be the moment of the birth of the universe.
So this is nice because this is actually very accurate, right? This is what we do. We make an impact at the beginning of the universe, then sound waves, or density waves propagate, and they show up at the last scattering surface that we see directly. Then we can use laws of physics to reconstruct what kind of impact we must have had in order to reproduce the pattern here, right? That's exactly what we do. So, you know, without a movie like this, it's impossible to explain this to the general public, but with this kind of movie, people get it. So here we go. It's the Planck temperature map. But topic of today's talk is not about the temperature fluctuation, but it's about polarization. So direction of the line represent the polarization direction. So that's where electric fields are oscillating with stronger strength than the other direction, right? And the length of the bar, length of the line represent the strength of the polarization. So this is all nice, right? Somehow cosmic micro background is polarized, but to quantify this, we have to somehow have a meaning to quantify the pattern. Yeah, there's a special pattern called E mode and B mode. So so this is, you know, if you heard about E mode and B mode before, you probably got confused and still confused and don't really know what we mean by this. I hope that today will be the last time that you get confused, okay? So I'll try to clarify everything that you might wonder about. So let's imagine a plane wave, okay? So for example, you have here this kind of polarization direction changes the direction, right? And if you had a plane wave, you know, like going this way, then you have, you know, blue, red, and the kind of thing, and then corresponding polarization directions, changing the directions. Now we want this here looks like a bunch of all the directions, but now we can decompose this into polarization directions parallel or perpendicular to the direction of the plane wave. This is E mode. If you have a 45-degree tilted version of that, it's B mode. So this E mode and B mode can only be defined in Fourier space. Unless you go to Fourier space, there's no way of defining this. And it's really, you have like let's say density waves. Okay, you have cold spot, hot spot, hot spot. Then you start looking at how these polarization directions are aligned or not aligned with the propagation direction of the plane wave in the sky. This is a two-dimensional concept. It's a two-dimensional Fourier transform. And then that's how we define E and B. And this decomposition is unique, and E and B are very important characteristic, namely E mode is a parity even, B mode is a parity odd. So if you do the inversion of a space coordinate, let's say L goes to minus L, then you see here E doesn't change, but B changes. B changes the sign, but E doesn't change. So B is indeed parity odd, E is parity even, and this makes E and B very special, okay? And here is the power spectrum. So x-axis is the Fourier wave number. As we go to the right, it's the small angular scales. If you go to the left, it's a large angular scale. And then let me actually explain to you, in case you haven't seen this yet. So this is the power spectrum. And if you go to the very left, you're looking at the fluctuation with the wavelengths that's as big as a full sky. Now you go to the right and you start seeing shorter wavelength fluctuations. And you keep going, right? Like decomposing sky into multiple wavelengths with various amplitudes. But then, of course, when you put them all together back, you will get the original image. So this is nothing but Fourier decomposition. Okay, now this part here is the power spectrum coming from the temperature anisotropy. This is E mode polarization. But this E mode polarization comes from the sound waves. So the same origin, okay? This creates this. Then this is B mode, but this is a B mode that's generated by converting E mode from sound wave to B mode by gravitational lensing. So all of these have the common origin. It's a sound wave. But that's not what we want today. What we want today is the B mode coming from the gravitational wave from the early universe. Now let me, so this hasn't been seen yet. All of these other things have been measured. And there's a 7 orders of magnitude in power, improvement in power in just 25 years. This is an amazing rapid progress of the field, right? If you think about it. And in fact, if you look at the approximate law experimental noise as a function of time, it's an exponential improvement. It's like a Moore's law. And this is very educational because here, to make this happen, you need to have microwave sensors, like tens of thousands of them. WMAP only had 10 radiometers, order of 10 radiometers. Now we have order of 10,000 radiometers, well, microwave sensors. And the next generation will have like 500,000 sensors. But if we weren't for cosmic micro background experiments, you would never need such number of sensors. Nobody wants to build so many sensors because you don't have any usage of those. But once people are convinced that cosmic micro background is a very, very useful tool to learn about the cosmology, technology really advanced exponentially. And now we have this kind of nice looking noise property. So this is very educational because it's often the case these days in cosmology, you go to conferences in cosmology and you present your exciting new calculations, which show you very small effects. And the audience might ask, well, might say, hey, it's too small to be seen. It's irrelevant observationally. Forget it, you know? But that's bad because if you look at this temperature sound wave fluctuations, right? This acoustic oscillation was predicted in 1970. Jim Peebles, for example, got Nobel Prize for it, and simultaneously Sneddon and Zeldovich predicted this, and they thought that this would never be observed, never. That's 1970. But then it was detected in 2000, so 30 years later. But then once people convinced that it's such a beneficial thing to measure, they go 7 orders of magnitude in sensitivity, right? Very rapidly, only within 25 years. So this is telling you that it's never too small. It's never irrelevant, okay? If the physics is good, physics is interesting, it's worth measuring, people get there. So the theorists' role is to calculate something interesting, you know, worth measuring. It's okay, it's too small now, but if it's interesting, people get there. Look at LIGO, right? I mean, how many years had to pass before they detect gravitational wave? But they get there. So I hope that young people are not afraid of calculating something small, very proud of that, in fact. And I also hope that senior scientists don't discourage them. You know, we may not have so many years until we retire, but they do. So don't discourage, no? Just actually, contrary, encourage them to bravely calculate something small. Okay? What comes next? So we had Kobe, Dabney, Planck, and also many ground-based and balloon-bound experiments to get us where we are now. Story continues. So to detect this B-mode polarization, multiple ground-based facilities are taking data today. And I wouldn't be surprised that tomorrow, for example, we will hear an announcement from any of these experiments claiming a detection of gravitational wave, the B-mode polarization from gravitational wave. So we want this. And in the next 10 to 15 years, right, we don't stop here. We want to spend another decade trying to measure this thing. And if ground-based telescopes see something, then we'll have a definitive measurement from space. So we proposed this LiteBIRD mission to JAXA with participation from USA, Canada, and Europe. So I'm in Germany now. I'm trying to assemble the team in Europe, especially in Germany, to contribute to this. This is the polarization dedicated mission with few thousand superconducting detectors in space. And we had a wonderful news that LiteBIRD has now been selected to fly. So we will go to L2, 2028, 2029, you know, it's pretty soon. Okay, so what do we learn with something like LiteBIRD, okay? So essentially we want to test this remarkable hypothesis that we all originate from small irregularities that existed in the early universe, okay? As you see in this movie, there was this hotspot, cold spot in the early universe, and they grow, perturbations grow gravitationally to form stars, galaxies, you know, planets, stars, planets, and eventually life on the planets. But ultimate origin is this cosmic micro background fluctuations. But then you ask, where do these cosmic micro background fluctuations come from, right? What generated the initial fluctuations? So the leading idea is a quantum fluctuation in the early universe, yeah? And you know, I see actually in the Zoom, I see, you know, your faces, but also a nice picture. I see actually picture of Alexei Starovinsky. It's very nice. So yeah, so he, you know, was one of the leading figures in this area, uses Stravinsky's name on top. So quantum mechanics was at work in your universe, right? There are quantum fluctuations in the early universe whose wavelength is of course very, very small, but then there's an exponential expansion in the early universe, stretching these microscopic fluctuations to macroscopic scales. And these provided the seed for galaxies, stars, planets, and eventually life. Now, is that really true, right? So that's what we want to test. To test that, we had a very good evidence for it already using cosmic micro background data, but extraordinary claims require extraordinary evidence. So we wanted to see gravitational wave also generated by quantum fluctuations during your early universe. So inflation predicts two things. One is the existence of density fluctuations called the scalar mode, zeta. Another is the gravitational wave or tensor perturbations. And we measure distortions in space. This is the distance between 2 points in space. You have a uniformly stretching factor, scale factor, but then you have perturbations. For example, this will be the perturbation to the determinant of the distance between 2 points. So this changes volume, right? This changes the volume or area, therefore this changes the density. This one here is constructed so that it doesn't change the determinant. Therefore, it's a transverse traceless metric tensor which would not alter density. That's why it's special. Yeah, it's an anisotropic distortion between points, between distances in 2 points. Okay, so how do we measure this thing? Well, you might know, you want to have a laser interferometer, so you shoot the laser from the left, you have a beam splitter, you send the beam to the above, send the beam to the right, beams bounce off, you recombine them here, but then the initial phase when you beam split is such that crest and troughs of the wavelength, the light waves will cancel, right? These two light lasers are shifted in phase. So when they're recombined, signal cancels and there's no signal at the detector. So that's your initial configuration. Gravitational wave propagates, stretches, right? Then suddenly distance between mirrors is different. So crest and troughs of the laser light no longer cancel. So you see the signal. Well, that's how LIGO detected gravitational wave from a binary black hole with a wavelength of thousands of kilometers. Essentially, it's the size of the Earth. And as long as you have detectors like LIGO on Earth, that's the maximum you can ever detect. And you can maybe send laser stations to space like LISA, and you can detect millions of kilometers, but it's not that much. This primordial gravitational wave affecting CMB has a wavelength of billions of light years today. So how can you ever find it? And in fact, because it has a wavelength of billions of light years, if you see it, it must be inflation. There's no astrophysical origin possible to produce such crazy long wavelength gravitational waves. So we use universe as a detector. You have a uniform isotropic electromagnetic waves called CME. You let the gravitational waves propagate through them. Then, because gravitational wave stretches space, wavelengths of the light is also stretched and squashed. So when wavelength is stretched, temperature decreases because wavelength is longer. It's a less energetic photon. When it's squashed, it's hot. Now you put electron, this electron will see hot photons coming from the above and below, but cold photons coming from left and right. Now let's imagine that light is coming from right and left and gets scattered by electron and coming toward you. Light from hot regions come and scattered by electrons and coming toward you. These lights are polarized in this direction. We have daily experience with this, more or less, if you are very careful. So you have the windshield of the car, and sunlight is coming from above. gets reflected by the windshield of the car. And then light gets reflected and coming toward you. This light is horizontally polarized. How do we know that? Well, let's say we have a polarized sunglasses that will transmit only the vertical polarization but block horizontal polarization, and you can see through the car. Okay? So what's important here, to produce polarization, you need to have anisotropic incident light. In this case, you have light only coming from the above. But universe is isotropic, so you can't have that kind of thing, right? Okay, sure, when you have a light that's coming from only one direction and gets scattered by electron, the light is perfectly polarized. But universe is isotropic. Around an electron, you have isotopic radiation. In that case, you don't have anything, no polarization. But if you had, like gravitational waves, right? Hot, cold, quadrupolar pattern around an electron, you create a polarization. This is what we are going to look for. You need locally anisotropic radiation pattern. So when gravitational waves are propagating from left to right, it creates around the electron. Okay, you have to imagine at each spot there's an electron. Electron will see temperature pattern looks like this because of the stretching of the gravitational wave. Then this will produce polarization pattern look like this. Yeah, so indeed, this is the K mode, right? Plane wave going to the right. Then polarization pattern generated by that is parallel or perpendicular to the wave vector. That's E mode. B mode, so you have now cross mode. Okay, you see gravitational waves come with two modes like this, yeah? So one mode produces E, another mode produces B. Let's put this into different context. So let's say you are in the center here. This is surface of lasso scattering. This is where CMB photons come from. There's a plane wave in the universe. Okay, this is the gravitational potential. Let's say, this is the gravitational wave going above. Okay, so there's a gravitational wave going from the below to the above. Then on this plane, because gravitational waves stretch only space perpendicular to their propagation direction, photons are stretched and squashed here. So white is hot, gray is cold. And as plane wave propagates, yeah, you see this kind of different patterns. An electron sees a quadrupolar pattern like that. So here you have hot, right? So you produce vertical polarization. And then you have vertical, horizontal alternating. And plane wave direction is obviously from bottom to up. So this is E mode. And when you have 45-degree tilted polarization of gravitational wave, you get B mode. Yeah. Good. So this is what we're after. And the important thing is that this can be produced not only by gravitational wave, but also by density waves, sound waves. But this can only be produced by gravitational wave unless gravitational lensing effect occurs. So that's why we showed here before that here you have the E mode coming from the sound waves. This is the B mode produced by gravitational lensing of this, but then this here is intrinsic B mode from the gravitational wave. So this is what we want to measure. Good. All right. Now, how do you produce this thing? Okay, so you have Einstein's equation, and you have the vacuum equation, right? So you have a Hij box that's equal to 0. And you quantize this equation and calculate the variance, and that variance is proportional to the Hubble expansion rate during inflation squared. And during inflation, Hubble expansion rate is nearly constant. So this means that this whole thing does not depend on K wave number. It's called a scale invariant, but this whole thing does not depend on scales. Once it's produced, it evolves according to this equation. So in Fourier space, this equation looks like that. So you have this 3 times Hubble expansion rate coefficient in the second term. This will modify the amplitude of a gravitational wave as gravitational waves propagate the universe, expanding universe. Then gravitational wave evolution is different whether this term is important or this term is ignored, okay? So you compare this term with that term. When this term is dominating over that, you have wave equation and you have an oscillating solution. Sub-horizon scales oscillating and the amplitude decays. But on super-horizon scales where this term is negligible, when wavelengths of the fluctuation is bigger than the Hubble length, this is the dominant term, and solution of this is that Hij is a constant. So there is this scale that separates the evolution. And very long wavelength gravitational wave, therefore, preserves the initial condition. It can actually allow us to directly probe the initial condition of the gravitational wave produced by inflation. But as you can see here, gravitational waves are produced at all wave numbers, all wavelengths. And once they are produced, they evolve, they propagate through the universe, they are redshifted by expansion, and amplitude of fluctuations get modified depending upon when they come back inside the horizon. So let me explain that. So first, this is the physical length in the vertical axis. This is a scale factor. So universe expands in this direction. This is the fixed wavelengths. So this will be the 1 megaparsec today. It's a megaparsec. 10 megaparsec today. 100 megaparsec today. 1 gigaparsec today. 10 gigaparsec today. Gravitational waves are produced at all wavelengths initially. Okay? And this is our horizon. They grow faster than just scale factor stretching the wavelengths. So if you wait long enough, these short wavelength fluctuations, which are once outside the Hubble horizon, they come inside. They are outside the horizon, they come inside. Outside the horizon, inside, yes, or inside. This is called entering the horizon. Now, notice that when they are outside the horizon, amplitude is conserved. They don't change. Once they become inside the horizon, they decay. Okay? So this modifies the evolution of gravitational wave. And if you plot the energy density spectrum of the gravitational wave today, depending upon whether they enter the horizon during the matter era or radiation era, they get the different red shifting. Then you get this kind of spectrum of gravitational wave energy density today. We haven't seen it yet, so this is purely theoretical. But important thing is, look, you have the frequency of gravitational wave coming from 10 to the minus 18 hertz to millihertz or decihertz and so forth here. You got 20 orders of magnitude, more or less, in the frequency coverage. You can measure by cosmic micro background here. It's billions of light years in wavelengths. Well, you have LIGO here. Well, you have pulsar timing array, nanohertz here. Okay? So depending upon the methodology, you are sensitive to different wavelengths of gravitational wave. And hopefully, we can measure all of these using different technologies. Okay? That would be really nice. But for this talk, we are focused more on this gravitational wave that will be seen by cosmic micro background. Yeah? So that's what we're after. So let me define so-called tensor to scalar ratio. So you have this variance of the gravitational wave divided by the variance of the density fluctuation. If this ratio is not 0, we say, aha, so we detected the gravitational wave. But so far, we haven't seen it yet. Current upper bound is 6%. But now you can have the tensor to scalar ratio in the vertical axis in so-called primordial tilt NS. That's another important parameter that we can use to test inflation models. I don't have time to explain it, but let's say there's another parameter. And then different inflation models with different energy density potential for scalar field predict different values of tensor to scalar ratio and primordial tilt. So we can say that we can exclude this model. We can also exclude this model, right? So we are really experimentally ruling out theories of very, very early universe. Yeah, so this is really, I mean, it used to be that if you work on inflation theory, you can write any theories, write papers, get cited, and get faculty positions. You can't do that anymore, okay? Your model has to be compared with data. If it's ruled out, well, you're not allowed to teach that model in the class anymore. We are not allowed to teach this anymore. This used to be the most popular model. Now, as time goes by, we exclude a bunch of models so that it seems like, you know, it's a difficult business now. But for example, Alexei Stravinsky's model, it's here, our square inflation, beautifully survives. So this now seems like a popular target for the next generation experiment. So with LiteBIRD, we want to improve on the upper bound on R by factor of 100 to go to the 0.001 level. And to this end, we have 15 bands, okay? Because, you know, I don't know if you remember, but at the beginning, I show you the microwave sky, and you see galactic plane in the middle. That galactic plane is also polarized. Thermal dust and synchrotron radiation are polarized, so we have to remove this dust and synchrotron foreground by having multi-frequency. From ground, you can't really have so many bands because of atmospheric absorption. But from space, we don't have that restriction. So we have 15 bands to remove foreground. But 15 bands is kind of many, very many, covering a factor of more than 10 in wavelengths. So we split wavelengths into 2 telescopes, actually 3. We have low frequency telescope, we have high frequency telescope. High frequency telescope is also split into 2. So this, we have 3 telescopes, 1 and 2 here. And this high frequency telescope is European contribution, low frequency telescope and launcher and bus system is Japanese contribution. And Americans and Canadians will produce detectors and readout system. So this is a really multinational, truly international collaboration. With that, we plan to measure power spectrum of gravitational wave, B mode. You see? This will be fantastic, you know. This happens, you know, I'll be so thrilled. Whenever we are struggling to, you know, calculate something or remove foreground, get drunk, you know, I look at this plot. I really want to see this. And then when Alexei Stravinsky is right, this is the constraint we get, yeah? This will be really nice. If nature is cruel and we don't see anything, this will be the upper bound. Then we can rule out a big chunk of popular inflation models that's shown by yellow. So ruling out this kind of class of models will be also a big deal for the fundamental physics, but you know, ideally we want to really see this kind of nice constraint. Okay, now if you listen to CMB scientists like John Sievers, yeah, for example, and telling you a wonderful story about B mode polarization, this is the end of the talk. But my talk doesn't end yet. I have only 2 minutes left, but you know, it's okay. I'm not gonna tell you whole story, but at least I wanted to tell you that there's a big missing piece here. I don't know if you noticed, but if you teach math to students and asked them to solve differential equations, okay? Differential equations have two parts, homogeneous solution and particular solution. And so far, we ignore the right-hand side of Einstein equation, the source. We set right-hand side to be 0. And we only look at the homogeneous solution. Now, if you only look at the homogeneous solution in math class, differential equation, you will fail, right? So up until very, very recently, right-hand side has been completely ignored by researchers studying gravitational wave production from inflation. But now, we are paying much more attention to this. And in fact, don't believe anyone if they tell you that detection of gravitational waves will be a signature of quantum gravity. Now, what do they mean by that? If you have no source, okay, this will be the quantum fluctuation in the gravitational wave. So gravitational wave is a space-time. So this looks like a quantum fluctuation in space-time. So that sounds like a quantum gravity, right? That's what they mean. But in order for us to say that, we have to show that whatever we detect in B-mode polarization comes only from the homogeneous solution. But if the properties of a gravitational wave are such that it's actually consistent more with a source, then we cannot say that it's coming from quantum gravity. It's something else. It's coming from the matter during inflation. So that's a new paradigm. So experimental strategy commonly assumed so far, you detect CMB polarization in multiple frequencies to make sure that it is coming from the CMB. Okay? It's not dust, it's not synchrotron, it's CMB. We have 15 bands or LiteBIRD to prove that. Now you check whether detected gravitational waves are consistent with scale-invariant spectrum. That's expected from the quantum fluctuation in space-time. If it is consistent, okay, you announce the discovery of the vacuum fluctuation in space-time. If not, you scratch your heads. Did I do something wrong? Or whatever. That's the commonly adopted strategy. Now I claim that this strategy needs to be changed. So first two are same. You make sure it's Planckian spectrum. The second is that it's a scale-invariant spectrum. The third, if it's coming from the matter fields, they can violate parity. They don't have to, but they can. Then you can have a cross correlation between E and B polarization, which violates parity, which wouldn't exist for vacuum fluctuation because vacuum doesn't care if it's left or right. But matter fields, for the weak fields, weak interactions, violate parity. So you can get cross correlation between E and B polarization that you can use to check parity violation. Also, matter fields, they can be completely non-Gaussian. If it's a vacuum fluctuation in space-time, it's most likely Gaussian. But if you detect non-Gaussianity, then you actually showing that it's coming from the matter fields. So if and only if it's Planckian spectrum, it's scale-invariant, no parity violating correlations, and Gaussian, then you can announce the discovery of the vacuum fluctuation in space-time. Otherwise, you may have just discovered a new physics during inflation. And this will be much more exciting. Now, if I say this, people tell me, oh, Eiichiro, come on, don't complicate anything. No way. But I would argue that these sources, matter fields, gauge fields, they are ubiquitous in high energy physics. In fact, if we don't have these things in inflation, universe will remain empty, cold, no reheating, no particles. So these particles must be there. I think everybody agrees on this. If they are there, they have every right to produce gravitational waves. And then this can really lead to rich phenomenology. You can now suddenly connect CMB, B-mode polarization with standard model physics, reheating, baryogenesis, leptogenesis, and so on. So it's a much rich system. Now I'm really out of time. Just to show you that we have calculation, okay? We have calculation, right? To show you that what I'm saying is not nonsense. And one thing that's very distinct, okay? It's a final take-home message is energy density spectrum of CMB. What you saw before was, okay, you get this and flat. If that's the case, it will be very difficult to see gravitational wave from LISA. LISA wouldn't be sensitive enough. But if it's coming from the source, you can have this kind of rising spectrum toward high frequency, which wouldn't be possible by vacuum fluctuation, homogeneous solution. If you have an inhomogeneous solution, it is actually more natural to have this kind of thing. Then suddenly you open up the possibility to probe inflation by both CMB and direct detection experiments. This would be really fascinating possibility. All right, and blah, blah, blah. It's very non-Gaussian and so forth. Yeah, so let me just summarize. So what I wanted to say is the next frontier in the cosmic microbackground research is to find primordial gravitational wave from the early universe. Now, inflation looks great. It's consistent with everything we see. But maybe, to really make the strongest possible case, find the definitive evidence for inflation, we would find B-mode polarization from gravitational wave. With LiteBIRD, we plan to reach 10⁻³ so 100 times better than the current bound. But I must tell you that before we fly this in 2028, 2029, I really hope that the ground-based experiments will see it, a hint of it. Then LiteBIRD will have a definitive measurement of it. Then we can really try to distinguish between the vacuum source and vacuum or the matter sources. This is very exciting. And then to enable this distinction, we have to not only look for scaling invariance of the spectrum, but also parity violation of chirality. Is that gravitational wave circularly polarized or not? And also non-Gaussianity. And this will open up the new research into the early universe. So I'll stop here. Thank you very much.
Thank you. That was a great talk. So we'll take some questions. So I don't think anyone's actually written on the chat box. So if you have any questions, okay. So Inji, I can see your hand up, but I just wanted to check if any students or postdoc, if you have any question for Eiichiro, just you can unmute yourself. Okay, Haidar, maybe you can go ahead.
Okay.
Haidar?
Yeah. Hi.
Hello.
Thank you, Professor Eiichiro, for your very nice presentation and your very beautiful lecture. Since yesterday, this is second time I am participating in your very interesting results on CMB and B modes, E modes, polarization, inflation, etc. So my question is about detection of B modes. If we be optimistic about the detection of B modes in near future, and also non-Gaussianity.
Yeah.
So as you said, it maybe can be considered as a improvement of the inflationary and quantum fluctuation of early universe evolutions. Am I right?
So if we find B-mode polarization from gravitational wave, it will be a definitive evidence for inflation.
Oh, okay.
Yeah, whether it's quantum fluctuation is a different question, but seeing gravitational wave primordial would be a definitive evidence for inflation. Yes.
Yes, I know. Thank you. But my question is about the reheating, preheating, and the end of inflation processes.
Yeah, good.
which usually, if we consider the standard model of inflation,
Yes.
cold inflation,
Yes.
we need to warm up universe by
Yes.
preheating and preheating processes
Yes.
to produce the particles and particles based on standard model of particle physics.
Yeah.
So it's confusing for me how we can make connection between the end of inflation and start point of inflation, because we know there is a problem of a very huge expansion, very rapid expansion of the universe in inflationary universe, and how we can consider this phenomena as a clue of inflationary universe. This fingerprints on CMB. Thank you so much.
Yeah. So usually reheating wouldn't leave much imprint in the CMB, but during, let's see, but during reheating, especially preheating, there's a violent nonlinear interactions of the fields. They produce copious amount of gravitational waves in high frequency here. Yeah. So not CMB, CMB will be here, but with other technologies, we might be able to detect gravitational wave coming from the reheating, preheating. That would be cool. But another thing is that this is much more indirect, but when you have scalar field coupled to gauge fields, for example, and these gauge fields can produce.
But sorry, Prof. My problem is that before preheating, maybe if I am I right? If I am, please correct me if I have confusing on this matter. My main is about the process of particles production, because before reheating and preheating, we have no any gauge fields and any particles, just inflation, for example, and other fields that run inflation. But after the end of inflation, the universe start fluctuations and start particle production based on preheating and reheating, based on quantum field theory, same like so. But before that, we have no any interaction. Am I right?
No, that's not correct. Of course, there are interactions. This inflaton has to be coupled to everything already.
But where? How? When we have no any particles, because we
do. All fields are already present. Okay, it may not be electromagnetic field because you would have to have a hyperfield, right? Instead
but
of.
We know, but sorry, we know because do this. Sorry.
No, look. Okay, if you have a standard model, let's say, okay, let's assume that standard model is correct up to very high energy scale. May not, but let's say. Then during inflation, action must contain all the standard model fields. Of course, they may or may not be coupled to inflaton, but they're there.
But my problem is that when we have a standard model of inflation, rapidly your universe desert, and so this very huge in amount in size universe, there is not make sense how we can make connection between these different fields in universe. But we should wait to the end of inflation.
That's right. That's
preheating correct. And reheating. But my main problem is about this Lagrangian, because when we consider this model for inflation, it's confusing me, really, honestly. It's a little bit complicated for me.
So let's say you have the standard model action, let's say it's there during inflation, but particles are produced but diluted immediately, so you don't see much. Once inflation ends, this inflaton gets converted into standard model physics particles because they are coupled, right?
That's right, yeah.
And they survive until today. But the interactions are always there. You see here interaction between axion and gauge fields. This is there during inflation too.
Yeah, actually,
It
my main problem
doesn't
is
suddenly
about
appear.
this interaction, Prof. Sorry if I have no time. I can summarize my question because I understand your very busy schedule. But my main problem is about this interacting term, because based on Linde model of inflation, chaotic inflation, new inflation, and also Starobinsky inflation, like so, we have to consider n is isolated inflation to have an graceful exit of inflation.
That's not true. That's not true. It doesn't have to be isolated. No.
But my references is are Linde, other leading professors in inflation. And if you let me, I can send my references to you directly.
No, but they write inflaton only just because they ignore all the rest. But the same Linde, same Stravinsky wrote the famous paper on reheating, right?
Yeah,
and they have, of course, couplings everywhere. So it's just that these couplings are not important during inflation, but they are there.
Yeah.
Unless they are there will be no particle production, right? So if you really wanted to be rigorous about it, you should keep all the terms even during inflation. And sometimes, depending upon the coupling, they actually do interesting things even during inflation.
Yeah.
And that possibility is, well known, old, but there's a renewed attention because these fields can actually produce gravitational waves during inflation, even before reheating. And that possibility is very new and exciting.
Yeah, thank you so much.
Yeah.
Okay, thank you. So we got two questions. So one from Injay and the other from Andrew. So I think Injay, you were before, so please, can you go ahead?
Okay, yes, very nice talk.
Thank you.
I think my question is that you mentioned about the at the last of your talk, this very interesting source, the matter field, possible matter field at early universe, which is described by this Lagrangian. I wonder, because at very early universe, the thermal energy of the universe is rather high. So what is the total energy of this matter field? Would that be comparable to the thermal energy, at a very early time? Because that would really determine how much that would give you an imprint on the microwave background, isn't it?
So typically during inflation, we think it's zero temperature, right? So there's no thermal energy, but there is inflaton energy, if that's what you mean. Energy density of the universe is dominated by inflaton energy, and true. These matter fields energy densities are much smaller than the inflaton energy density. Otherwise, inflation stops, right? So you want to make sure that the universe is still dominated by inflaton energy, inflating. But the thing is, even if matter fields have very small energy density, their energy density is big enough to produce detectable gravitational waves, right? These are different things. Gravitational waves have tiny energy density also, and they are still detectable. That's the key.
So is this, if you can see the screen, is this lambda tunable parameters? Like
it is tunable phenomenologically, but fundamentally it's really not tunable. It's order unity.
Okay, I see. Yeah. And the last thing is this can this one be responsible to basically initiate the preheating and matter production at the end of inflation?
Yes, yes, that was a connection I was alluding to. Right, this is which phenomenology is possible, and suddenly you have connection between gravitational wave and reheating. Yeah.
Yes.
So that's really fascinating new possibility.
Yes, indeed. Yeah. Yeah, I do have other questions. So maybe let's Andrew goes, and then later on, if time, then so let Andrew goes. Yeah.
Yeah. Okay. Andrew, you can go ahead.
Can you hear me?
Yes.
Okay. First of all, great talk. Thanks so much for presenting this. Very exciting. I have a kind of practical question about foreground subtraction.
Yes.
Of the LiteBIRD mission.
Yeah.
You mentioned how you're sort of going to use these different bands to do some foreground subtraction, but obviously, well, I'm assuming there's a lot more you have to do, right? You have to model really the the spatial distribution of,
yes.
of the electron and the polarization and everything. And
yes.
so what's the strategy for doing the foreground modeling and foreground subtraction?
Yes, thank you for asking that. So we have a strategy, different strategies depending upon the multiples. For higher multiples, so the challenge is really that the foreground properties change from place to place in the sky on large scales. But for small angular scales, it seems that the foreground properties are simple enough to use, for example, internal linear combination methods. So they seem to work pretty well on L's greater than, let's say, 50 or 100. So that's good. But what we are really targeting is the low multiples because it's a satellite mission. For that, indeed, we would have to model the physical properties of the foreground and use the maximum likelihood method to estimate tensor to scalar ratio, simultaneously determining the foreground properties, which are spatially varying. Yeah. So we don't assume constant ACD of the foreground over the sky. We actually subdivide the sky and then do the fit in pixel by pixel. Big pixels, but still spatially varying ACDs are fully taken into account. And our study shows that we can go down to R over 10 to the minus 3, but probably not much less. So we might ask, okay, LiteBIRD can go to R over 10 to the minus 3. Can we imagine going to 10 to the minus 4? The answer is yes, if we ignore foreground and only talking about detector sensitivity, then we can totally go to 10 to the minus 4. But because of the foreground, I don't think we can ever go to 10 to the minus 4. So 10 to the minus 3 would be, I think, is a realistic fundamental limit for R imposed by galaxy. Now, in future, next generation humankinds, or whatever kinds, it doesn't have to be human, if they manage to create a CMB satellite mission that can go outside of Milky Way, then suddenly they have the very clear sky, right? No foreground. Then they can go to arbitrarily small r. Yeah, so they will have fun, but not us, unfortunately. We can't go outside the Milky Way.
Okay, so this is a caveat on your initial encouragements of don't worry about going too small. If you have to go to R to the 10 to the minus 5th, that's too small, I guess.
Oh no, you misunderstood me. I said, right? In the next generation, whatever kind, doesn't have to be humankind, they will do that and they read papers. They still keep papers from us.
Okay.
So your paper, talking about R to the minus 5, you'll be cited, thousands of times then, right?
Right.
Yeah. No, I still keep my words. No, don't be afraid of publishing. There are papers, for example, when you have second order sources like scalar fields or matter fields, even large scale structure, they produce gravitational wave by second order, and they actually correspond to R of 10 to the minus 6, 10 to the minus 5. Who knows? Eventually that may be detected, and those are beautiful papers. Certainly people should be encouraged to write these papers. If physics is right, physics is beautiful, do publish.
Thanks for this immoral encouragement. Look like I will work very productively posthumously.
yeah, of course.
Okay. So just my another question just follow this related to this. I mean, you mentioned 10 to the minus 4 would be the limit due to the foreground, or let's say due to the incapable of flying out of our own galaxy. I wonder, but there is a cosmic limit, cosmic variance, and there is also the lensing, confusion as you've shown.
Yes.
So just be realistic. Let's don't have those science fiction, but to be on the ground and with really low technology, bolometer temperature, what is the limit you might get? Is that 10 to the minus 3?
So no, that will be much lower. here lensing can be removed. Lensing can be removed from the pixels. So that wouldn't do anything. And if there's no, I mean, cosmic variance doesn't exist for detection. If you're only looking at detection of things, there's no cosmic variance term. Cosmic variance characterizes how well you can measure the amplitude is, for example. That's cosmic variance. But cosmic variance doesn't limit, So that is totally fine. So fundamental limit, interestingly, right? I just said, if you have a second order scalar perturbations, they produce R at the level of 10⁻⁵, 10⁻⁶. That will be the fundamental limit, right? Below which you can't just go, right? So the cosmic variance of that scalar modes would give you the ultimate limit. Also, there's something else that's interesting. You have cosmic reionization. You have reionization bump here. Reionization is not homogeneous. They actually have spatially varying optical depths. Spatially varying optical depth modulate E mode polarization to produce B mode polarization. It's similar to lensing, but it's coming from the patchy reionization. This produces B mode, again at the level of 10⁻⁵. So those will be the limits then.
But when you measure the map, it doesn't have a cosmic variance. But when you use that map to constrain the parameter of R, then there is a cosmic variance. Right?
That's correct. Because that's correct.
So that limit is, you say, is below 10⁻�3. So it could go as low as 10⁻⁴.
Yeah, that's right. So if you, that's right. So you let's say you measure R of 10⁻�3, and then the error bar on R, right? That's cosmic variance. And that will be, some fraction of 10⁻�3. Yeah.
Okay, I see. Yeah. Okay. That is what I expected. So you won't get a huge signal noise on 10⁻�3 level. I mean, you might see something, but it might not be decisive.
You will. I mean, like, detection can be many sigma. Okay. Detection can be 10 sigma. But the error bar on R may not look like 10 sigma because of the cosmic variance. Yeah. But the detection itself, because what I'm saying is that let's see if I can write anything here. Text. How does it work actually? The row. Yeah, there you go. So let's say you have here R, and then likelihood. Likelihood. Yeah. Then this is 0, okay? And likelihood looks like this, okay? So this is cosmic variance, yeah? But you can totally exclude 0 by high significance, right? You don't know what the actual value is because of cosmic variance, but you can totally exclude 0. Right? So here, there's no cosmic variance. So if you wanted to claim a detection, you don't have any cosmic variance.
Okay, I see. Okay. And what is the technology limit, like the bottom of technology? Would that determine how cold your bolometer measurement would be? You just, I mean, for instance, LiteBIRD, ambitious LiteBIRD, would you just technologically, in terms of technology, you just trying to cool your bolometer as low as possible? And what is that?
You don't need to cool that much because these are superconducting detectors. So as long as materials are at the superconducting level, then you don't need to cool any further. So our detectors are kept at the temperature of 100 millikelvin, so 0.1 Kelvin, and that's sufficient. We don't have to go below that. And now, if you are in space, the biggest source of the noise is actually short noise of CMB photons. Okay.
Oh, interesting. Okay.
Yeah. So these detectors are background limited. So for each detector, you cannot do any better because you're already photon noise dominated. The only way to improve the sensitivity is to have more detectors. So we have 4,000 detectors in space. You can have 40,000 detectors if the ESA, JAXA, NASA, Indian funding agency, whatever want to pay us, Chinese, funding agency. So collectively, we instead of having a $500 million mission, that's LiteBIRD, we can have $10 billion mission, lot more detectors. Then we can arbitrarily low in sensitivity, in noise level. So that's not an issue at all. Yeah.
Okay, so it's mainly money limited.
Yeah, that's right. But eventually it's the foreground that kills you. Yeah, for now.
Yes, I believe. Yeah. Okay. Yeah. I think. Yeah. So I do actually. I mean, I asked 3 of this. I still have 5. So, but this will take much longer time. If you have a time, I can. Do you have a time after this? I just quickly chat you on.
Sure. Yeah. No problem. Yeah. Sure.
Yeah. The other people may sign off. So Momita, you might just announce finish. So I will just have a.
Okay, but I just wanted to ask if anyone else have any questions. Any other participant, if you have a question, now is the time, because otherwise Injay will dominate.